All right, so our next video is going to deal with things called mixtures. Mixtures are not pure substances. Why are they not pure substances? It's because I've taken a bunch of stuff and put it together. And I can take it apart. And I can take it apart pretty easily most of the time. So it's a mix of different substances and it's not considered pure. When I make a mixture, I am mixing things physically, but there's no chemical combination. So think of something as simple as salt and pepper. If I put salt together with pepper, uh, I mix them all together. That's a mixture, but I didn't do anything to the salt or the pepper. So I could still go in there, find a piece of salt. It tastes like salt. I could still go in there, find a piece of pepper. It tastes like pepper. So the chemical properties have not changed with what is in there. So there you go. Got a couple examples. Have a couple different types of mixtures. The first one is called a heterogeneous. Hetero always means different. Um, so substances are mixed uniformly, but not evenly distributed. So basically, there's not a great um, mixing of them. Um, if you were to think of putting muddy water, you put dirt into water and try to mix it all up. Well, guess what? That's going to be heterogeneous because the mud hasn't spread itself out evenly throughout that mixture. Um, Oil and water. Okay, oil and water don't mix. So when I put them together, they don't mix. They actually create layers. So that's a heterogeneous mixture. This thing about immiscible liquids. Immiscible liquids is liquids that basically don't mix. Okay, so the water and the oil are immiscible there because they're not mixing. They're not creating a nice even mixture throughout. A homogeneous mixture, homo meaning the same. The components are evenly distributed and the mixture is the same throughout. So it's going to have the same consistency throughout the entire mixture. So the opposite of immiscible liquids would be miscible liquids. So if gasoline's an interesting one. Gasoline, there's stuff in there, but when you pour it, it just kind of looks um, the same throughout. It looks uniform throughout. That's because it's a homogeneous mixture with miscible liquids. The stuff in there, the components of that mixture will not settle out and will not create differences throughout it. Sometimes you can mix different types of things. So, for example, gases can be mixed with liquids. If you've ever drinking a pop, you have drank a homogeneous mixture. What is that? What is in that mixture? Well, it's got sugars in it. It has flavoring. So, if you drink a Pepsi, it tastes different from a Mountain Dew. And it also has carbon dioxide. So now I'm mixing a different type of substance, a gas, dissolved into that water. And it's homogeneous throughout, meaning it's the same throughout or it's spread evenly throughout. So, a couple pictures here of some mixtures and substances. So pure substances, you have elements and compounds, mixtures, homogeneous and heterogeneous. You see homogeneous, these things are kind of spread evenly throughout. See heterogeneous, the purple kind of clumped in different areas. Up here you see that in this heterogeneous mixture, the what we call these bluish are settling to the bottom, whereas in a homogeneous mixture, everything's spread evenly throughout. Okay, so we're going to deal a lot with these different types of mixtures here throughout this unit. When we talk about mixtures, the three most important type of mixtures we worry about are these things: solutions, suspensions, and colloids. A solution is exactly what I just talked to you about: pop, seawater, iced tea with sugar in it. These are solutions. It says a mixture in which one or more substances are uniformly distributed in another, or basically they're distributed evenly. Or another way to say it is something will dissolve out. All right. If I take a glass of iced tea and I put sugar into it, sugar will dissolve in that, and hopefully every drink of that tea will be a little bit sweet. Okay, now I did not have a chemical reaction. That's why you can still taste the sugar and you can still taste the tea. So those still have maintained their properties, but one has dissolved in the other. Okay, when we talk about a solution, we have these things called solutes and solvents. A solute is the substance that is dissolved out. The solvent is the substance in which the solute dissolves in. So I know there's one example on the slide here, but think of my iced tea example a moment ago. If I have a glass of tea and it's not sweetened, I'm at the restaurant and I like it sweet, I put sugar into it and I stir it up. That sugar dissolves out and spreads itself out evenly throughout that tea, hopefully, and therefore every drink of tea will taste kind of sweet. The sugar is the solute, solute, because that is the stuff that is dissolving in the tea. The tea, in that scenario, is the solvent. The solvent is the stuff that the solute dissolves in. Most solutions, the solvent's going to be water, and we call that an aqueous solution. It says any solution in which the water is the solvent, that is called an aqueous solution. You can have different concentrations of solute. So if I put a 1 sugar packet into my tea, it may be kind of sweet. So I have changed the concentration there. If I put 10 sugar packets into my tea, it has become more concentrated because I've added more solute into that tea. When a solution becomes saturated, no more solute can be dissolved out. So if I keep adding sugar and sugar and sugar and sugar into that tea, eventually that sugar is just going to settle to the bottom because there's basically not enough room for it. It's become oversaturated. And you're actually going to do a lab when I get back about the saturation in the solution. The suspension. A suspension is a mixture. Again, all these are mixtures. They're not pure substances. So a suspension is a mixture where the materials will not dissolve. If you've ever had Italian dressing is that dressing, you shake it up and you get all these particles floating around in it. But once you set it down and let it sit there for a while, all those particles kind of settle to the bottom. That would be a suspension. So in a suspension, the movement of that mixture actually keeps the materials floating around and mixed throughout. But once the movement stops, it settles to the bottom. Um, it's kind of like a creek or a river. A river will carry a bunch of stuff with it, making it a suspension. But if somebody turned that turned that water off and made the water stop, all those sticks and rocks and mud will settle to the bottom because the movement has stopped. That would be a suspension. You can see a couple other examples there. Muddy water, hot cocoa, sort of. Sometimes you'll have hot cocoa. That'll be a nice, neat solution for you. When you see these things, this talks about the size of the particles. Normally, in a solution, you have very small particles. This nm is in a nanometer. Okay, we'll discuss that while in class together. But you see the particles in a solution are really, really small. The particles in a suspension are pretty big. In a colloid, this is a little bit different. Mixture in which microscopic solutes are dispersed in another substance. They will not separate, but they're not going to dissolve. Kind of a weird thing to say here, but basically they're spread throughout, and these particles are intermixed with each other all throughout, but there's no dissolving going on. Milk is actually a colloid. A good example is fog. Fog is basically all these little particles that are spread throughout um, the air, but they're not really dissolving in the air, but they create this weird looking appearance. So colloid, the size of the particles is actually somewhere between suspension and solution. Colloids are confusing, and we'll have better discussion about those in class together. This is an interesting thing. If you take a solution, a suspension, and a colloid, and you shine a flashlight through them, you'll get something that looks like this. We will not be able to see the light through the solution because all those molecules have dissolved out. So it kind of blocks the light. In a colloid, the light will be able to shine through it. Then in a suspension, you'll shine the light and you'll see all these little particles floating around. And again, the colloid's probably the most confusing one there. I think shaving cream is another example of a colloid and how these particles don't dissolve out. And I am not going to play this video for you. When it comes to how concentrated something is, we talk about the solubility of it. So the maximum amount of a solute that can be dissolved in a solvent at a given temperature. So how much can dissolve out? It says solubility increases with increased temperature. When I was young, we made iced tea all the time, but in order to make the tea, you had to first boil the water to put the sugar in. The reason we had to boil the water to put the sugar in is the higher the temperature was, the more sugar you could dissolve into it. So my dad loves his, they call it Southern sweet tea. Southern sweet tea has a ton of sugar in it. When you heat it, we're able to get more sugar into it because the solubility has increased. Already mentioned this, a concentrated solution. This is a solution in which a large amount of solute is dissolved out. If it's dilute, there's very little. So, think of my iced tea example. If I just put a little pinch of sugar into it, that's a very dilute cup of tea. Kind of keep mentioning these same terms here. Saturated solution. If it's saturated, it contains all of the solute it can hold at a given temperature. I'll give you an interesting example. My yard holds water. It doesn't drain real well. So after it rains, I go out. It's really soft and soggy and muddy. It's become completely saturated with water. Okay. Or basically, it can't hold any more water if it rains anymore. I'm going to have puddles all over. That's the same thing with a saturated solution. It's got as much solute in it as it can hold. And when that happens, it cannot hold anymore. And you're going to start seeing that solute start to fall to the bottom and not dissolve out. If it's unsaturated, more solute can be given to it. Super saturated, you're going to actually make rock candy next week. But this contains more solute than what a saturated solution can have. So you may be wondering how is that possible? Well, you're going to have to force it to make a super saturated solution. So again, back to the tea example, I put sugar in, sugar in, sugar in, sugar in, and start settling to the bottle. But I keep putting sugar even after it becomes saturated. There are ways that you can make that solution hold it, and that has to do with this. So saturation can change in a solution by doing a few different things. Number one, if I stir it. So even if I have a ton of sugar in that iced tea, if I keep stirring and stirring and stirring and stirring, I could probably get more sugar to fit into it. Sometimes if I change the size of the crystal, if I just put one big sugar cube into that tea, it may have a hard time dissolving out. But if I change the size of that crystal or I make the sugar smaller and smaller and smaller, it'll make it be able to dissolve out because those water molecules are binding to that sugar a little easier. And then finally, temperature. If I heat it up, I'm going to be able to dissolve more out as I go through it. And we're going to do a couple different labs that show how this process works while we're in class together. Saturated, unsaturated, super saturated. You see here, unsaturated doesn't have as much stuff in it, and everything is dissolved. If it's saturated, the molecules may be dissolved, but no more will fit in. Basically, I've reached my highest point that will allow it to dissolve. If it's super saturated, what do we see here? I start to see crystals forming. And this is the lab I was telling you about where you're going to make rock candy. And that is it for that video.